Hello, everyone. Today we'll be talking about plate tectonics. So let's get started. So, what is plate tectonics? So, the asthenosphere is what we've learned about in our previous classes. That's referred to as plastic, meaning it's somewhere in between a solid and a liquid, kind of like a gooey feeling. And because it has that texture, it's able to have convection currents. And these convection currents are driven from the heat coming from the inner core, as you can see here. So, since we have convection currents in the asthenosphere, which is part of the mantle, the lithosphere on top, that's the crust and the top part of the mantle, it starts to move with these convection currents. And that is what we call plate tectonics, the movement of the plates. Plates are just pieces of the lithosphere. So, let's go over some vocabulary. Tectonic plates are pieces of the lithosphere. And as you can see, we have many different pieces or plates of the lithosphere. This is the Australian plate, African plate, Eurasian plate, North American plate. And plate boundaries are the boundaries between the plates or where the plates move. So sometimes the plates move away from each other. That would be a plate boundary. Sometimes the plates slide past each other. That would be a plate boundary. Then sometimes the plates move towards each other. I don't think this diagram shows that. So let's write that down. Pause the video if you need to. Plate boundaries, Earth's interior creates plate boundaries, and plate boundaries are caused by convection in the asthenosphere, which is part of the mantle. So let's talk about the types of plate boundaries. When two plates meet or collide together, we call that a convergent plate boundary. Let's write that down. So one of the types of the plate boundaries is a convergent plate boundary, and that's when two plates collide or meet. Now, recall from our previous lessons that the oceanic crust is more dense and the continental crust is less dense. So that means that if I have a convergent boundary where two plates are meeting or converging or colliding, and if I have an oceanic plate colliding with a continental plate, the oceanic plate will sink because the oceanic plate is more dense. So remember, plate is a piece of the lithosphere, which is the crust plus the upper mantle. Now, when the oceanic plate sinks, it comes in contact with magma. It starts to melt, and the heat causes it to rise up or even explode into a volcano. So, we know that in convergent plate boundaries, we can form volcanoes. This can also cause really huge earthquakes to form. So another thing that forms is a trench, as you can see right here. So a trench is a long, narrow dip, as you can see, or a depression in the Earth's crust. So when an oceanic plate sinks under a continental plate, we also create a trench. And you can see this in this picture as well. An oceanic crust and the continental crust are converging or coming together, and the oceanic crust sinks because it is more dense. That causes it to melt and rise, forming volcanoes. And the convergence can also create a trench, which is a narrow dip. Now, what happens if a continental and a continental plate collide? If two continental crusts or plates collide or come together in a convergent boundary, they both have the same density because they're both continental crusts. So, what's going to happen is they're going to both rise, creating these mountain ranges. And what happens if two oceanic plates converge or collide? Well, the thing about oceanic crusts is that as an oceanic crust becomes older, it actually becomes more dense because it gets colder over time. We'll talk about why it gets colder over time in the future, but older oceanic crust is actually more dense. And because of that, if two oceanic crusts meet, the older oceanic crust will sink or subduct. Subduct is another word for sink. And it will create about the same effect as if an oceanic crust sinks under a continental crust. It will melt, rise, and form volcanoes and even earthquakes, as well as trenches. So let's write down the structures that are formed by the convergent boundaries and some natural disasters as well. So we learned that convergent boundaries create trenches, they create mountains, they create earthquakes, and they can even create volcanoes. This is a picture right here of a trench. When the oceanic crust sinks under a continental crust, we create a dip called a trench. Pause this video to write these notes down. Now, another type of boundary is called a divergent boundary, and this is when two plates will move apart from each other as opposed to coming towards each other like a convergent boundary. So let's write that down. Another type of boundary is a divergent boundary, and that's when two plates are moving away from each other. Pause this video if you need to. So, what happens when two plates move away from each other? The first thing we're going to form is a rift valley. So, a rift valley is a lowland region, as you can see here, that forms where Earth's tectonic plates move apart or away from each other. This is something we also call rifting. That's another word for it. And it can happen in the land as well as the ocean. So when two continental or oceanic crusts will move away from each other, we form this another type of dip, and this is called a rift valley. And this is an image of the African or East African Rift Valley, as you can see here. Now, another thing a divergent boundary will form is a mid ocean ridge. And this image shows what a mid ocean ridge looks like. So, if two crusts move apart from each other, it creates a gap in the middle, as the image shows, and that creates a pathway for the magma to rise up. As the magma rises up, it actually creates tiny mountains or even volcanoes, and that is what we call a mid-ocean ridge. So a mid-ocean ridge is a continuous series of underwater volcanoes or mountains. A mid-ocean ridge requires the ocean to be there, so this normally happens in the ocean or beneath the ocean with two oceanic crusts. And this is another image of a mid-ocean ridge. So we have convection currents in the magma. When two plates move apart from each other, when two oceanic crusts move apart from each other, the magma has a gap to rise up from. And this gap, what happens is the magma rises and cools to form volcanoes and even mountains. And this GIF also shows what happens. The magma is rising, and what happens is that the magma, as it rises, it cools down, and notice the cooling effect creates new rocks to form or new land to form, new crust to form. If magma solidifies, cools and solidifies, it's actually creating igneous rocks. Remember, igneous rocks require cooling and solidification, and that's what happens in a mid-ocean ridge. We're creating new crust as the magma is rising under the ocean. We also call this seafloor spreading because as the plates are moving apart, our sea floor, this floor beneath the sea, is actually spreading apart because not only are the plates moving away from each other, the magma rising is creating new crust to form. So we're increasing our sea floor and spreading our sea floor. And notice that the newer crust is in the middle where the mid ocean ridge is, and the outer parts of the mid ocean ridge, as we go farther away from the mid ocean ridge, our crust is getting older. This is another example or an image of a mid-ocean ridge. Notice that where the mid-ocean ridge is, we get our youngest rocks or youngest crust because the magma is cooling and solidifying to create new crust. And as we move away from the mid-ocean ridge, these are our older rocks that once upon a time used to be here, but the ocean floor is spreading. The mid-ocean ridge, an example would be the mid-Atlantic ridge, as you can see here. This ridge is underwater. Here's another image. The mid-Atlantic ridge formed in pretty much the same way. The North American plate and the Eurasian plate moved away from each other, creating a gap for the lava or magma to rise. And the rising of the magma causes it to cool down, solidify, creating mountains and volcanoes. So let's review or write down the notes for what structures are created by divergent boundaries. So divergent boundaries create rift valleys, mid-ocean ridges. It creates seafloor spreading, meaning our seafloor is spreading, and this causes it to create new crust. This image also shows that near the mid-ocean ridge we have younger rocks, and away from the mid-ocean ridge we get older rocks. So pause to write this down. Now, let's talk about the Earth's magnetic field. So we already know that the Earth has a North Pole, a geographic North Pole, and a geographic South Pole. Um, this is what we refer to as the North Pole versus the South Pole. But the Earth also has a magnetic field. So if you imagine the Earth to have an imaginary magnet inside it, that magnet also has a North Pole and a South Pole that's different from the geographic North Pole and South Pole that we're used to. So, as you can see, the Earth has an imaginary magnet inside it. It's not really a real magnet, but it does create a magnetic field. Then that magnetic field has a north end and a south end. So, this magnet or imaginary magnet has a north magnetic pole and a south magnetic pole. The Earth has a geographic North Pole, geographic South Pole, but also a north magnetic pole and a south magnetic pole. This is a clear image. So, this is an imaginary magnet, and the Earth has a south magnetic pole for that imaginary magnet and a north magnetic pole for that imaginary magnet, and it creates a magnetic field. Now, you may be wondering how come the north magnetic pole is facing the geographic south of the Earth, but the south magnetic pole is facing the geographic north of the Earth? That's because every 600,000 years or so, the Earth's magnetic pole, that imaginary magnet, reverses or flips. So today, it looks like the south end of the imaginary magnet is pointing towards our north or geographic north, and the north end of that imaginary magnet is pointing towards the geographic south. However, in 600,000 or about that many years, our magnet or imaginary magnet will flip, and that will cause the north magnetic end of the imaginary magnet to point towards the north, our geographic north, and the south magnetic end to point towards the geographic south. And it will reverse again in another 600,000 years or so. And this keeps happening over and over again, where our Earth's magnetic field flips or reverses. So, how does that have an impact on our rocks? Let's see. Magma is made up of many minerals. Some minerals can be magnetic. So, if something is magnetic, it will follow that Earth's magnetic field or the Earth's magnetic poles. Okay? So, as you can see here, if I have a rock and I have minerals in that rock, the north end of those minerals will point towards the north end of the Earth's magnetic field, kind of like a compass or an actual magnet. And if my Earth's magnetic field reverses, so my Earth's magnetic field is pointing this way, but if it flips and the north end of the magnetic field is towards like this, then my minerals, the magnetic minerals, will also follow that direction. They will point towards the Earth's magnetic north. So, recall that as oceanic plates move away from each other, magma is coming up, solidifying, cooling down, and creating new rocks, right? Now, if those rocks come up right here and solidify during a normal magnetic Earth's normal magnetic field, as you can see here, where the south end of the magnet is pointing up and the north end of the magnet is pointing down, those rocks or minerals, magnetic minerals within the magma, will point towards the Earth's magnetic north. So this image is kind of showing that. Let's see. The red part is the Earth's magnetic or the north end of the minerals, right? The north end of the minerals will point to the Earth's magnetic north during that time. Now, 600,000 years later, my Earth's magnetic pole or that imaginary magnet will flip. That means my rocks or the minerals within the rocks that are magnetic will also flip to point towards the new magnetic north. This creates a pattern, as you can see here. So as we're creating new rocks, some rocks will point towards the Earth's magnetic north at the time, but if the Earth's magnetic north reverses, the other rocks will point towards the other side, pointing towards the Earth's magnetic north at the time. So every 600,000 years or so, as we're getting new crust in the mid-ocean ridge, that new crust will point towards the Earth's magnetic north at that time. After 600,000 years or so, when we're getting brand new crust again, that brand new crust will point towards the Earth's the new position of the Earth's magnetic north, and so on. If you look closely, this is my mid-ocean ridge. Each side of the mid-ocean ridge is symmetrical. So, a question you might get on the regions is this: base your answer to the following questions on this diagram. The diagram represents a pattern of normal, which is the gray, and reverse polarity. Okay, meaning in the normal polarity, my magnetic north of the earth was pointing a certain direction, but in the reverse polarity, my magnetic north of the earth has reversed to a different direction. And the rocks are showing that they were pointing to where the magnetic north was at the time. Now, complete the diagram by shading the pattern of normal polarity on the west side of the ridge. All you have to do is make sure this side is symmetrical to this side. The answer would look something like this. So you would shade this in. If my magnetic north or my minerals point a certain direction here, it should still point a certain direction, that same direction here. So we shade that in. But if my minerals pointed a different direction here, it should point in a different direction here. The gray and white are showing normal polarity versus reverse polarity. All you need to remember is each side of the mid-ocean ridge should be symmetrical. Now, our last plate boundary is a transform plate boundary. And in a transform plate boundary, the plates slide past each other. Let's write that down. Pause this video. So, our last type of plate boundary is a transform boundary where plates slide past each other. So, what does a transform boundary form? In a transform plate boundary, as the plates slide past each other, the plates actually create a crack in the crust. This is what we call a fault. A fault also means crack, but I would like you to use the word fault. We use the word fault for this. And this crack happens when in a transform boundary when two plates slide past each other. And a fault like this can lead to earthquakes but not volcanoes, because for a volcano to form, the crust needs to be pushed down or the plate needs to be pushed down towards the magma so it melts and thus rises. But this doesn't happen here. So faults typically just create earthquakes. And this is an example of a fault. It's a San Andreas fault that crosses all throughout California. As you can see here, it's huge. And this is another image of the fault. It's 750 miles long. And this is a major cause of why California gets earthquakes. Let's write that down. Transform boundaries, create faults. Now, let's put everything together. The diagrams below show where most earthquakes and volcanoes happen, right? And if you compare these two diagrams, you'll notice that most volcanoes and earthquakes of the world happen where the plate boundaries are, where the plates are moving either towards each other, away from each other, or sliding past each other. And this diagram also shows where my divergent boundaries are, where my transform boundaries are, and where my convergent boundaries are. Notice that in your note packet, we only wrote earthquake for the convergent boundary. Earthquakes happen in all the different types of boundaries, but for convergent boundaries, we have the largest earthquakes. And that's about it. Thank you.